We now want to quantify this position where the Gibbs free energy reaches a minimum value, or the slope is zero when the temperature and pressure is constant, and we would like to determine the composition of our equilibrium mixture at that point. The change in Gibbs free energy, according to our fundamental equation for closed systems with no chemical reaction, is given by this fundamental equation that we derived in previous lecture slides. However, if there is a chemical reaction, we need to add another partial derivative in order to calculate the total change in the Gibbs free energy. And that is how the Gibbs free energy of the mixture will change if the pressure and the temperature stays constant, sum over all the components which the number of moles change due to that chemical reaction. Another definition, this term here, which says how does the total Gibbs free energy of the mixture, this is the total number of moles in the mixture, how will this total Gibbs free energy change with a change in the number of moles of each specific component, gives us the chemical potential of that component. If you want to see it that way, what is the potential of that component to change the Gibbs free energy in the mixture if its amount in that mixture should change? So we want to evaluate this expression once the part where the pressure and the temperature changed, that part of the path is already considered, and we are only interested in the change in Gibbs free energy due to the chemical reaction. From our definition of the reaction coordinate, we can replace the dN, the change in the number of moles, in terms of the stoichiometric number of each component in that reaction, in that reacting system, as well as differential change in the reaction coordinate. So therefore, with no change in pressure anymore, no change in temperature, our total change in Gibbs free energy for that part of the path with all our substitutions can be expressed as the sum of the chemical potential of each component multiplied by its stoichiometric number multiplied by the differential change in the reaction coordinate. Since this is an exact differential equation, it implies that this term is the slope or the partial change of how the Gibbs free energy change with epsilon, or the reaction coordinate, when the temperature and the pressure is constant. At equilibrium, we know that we want this slope to be equal to 0. And therefore we know that the sum of the chemical potential of each of the components multiplied by its stoichiometric number must be equal to 0 at equilibrium. The chemical potential of each component in the mixture is a function of the composition at that point. And it is given by this rather scary looking expression over here, which says that its chemical potential is a function of its Gibbs free energy at its standard state plus RT ln, and now this is the fugacity of the component in the mixture, divided by the fugacity of the pure component at the standard state. So no, you did not miss any lectures. The main concepts behind the theory of the fugacity and the standard state fugacity and the chemical potential is actually discussed in chapter 11 and chapter 12, which will not be considered in this course. So in this course, we will treat the concepts on a need-to-know basis. The first is the concept of the standard state, which refers to the particular state of a species at a temperature T and at specified conditions of pressure, composition, and its physical state, whether it's a gas, a liquid, or a solid. The standard state pressure is either 1 atmosphere or 1 bar, 1 atmosphere the older version, 1 bar more modern. For our purposes, it's not really going to make a big difference. And of course, for the standard state composition, we are going to consider pure components. For gases, the ideal gas state, and for liquids and solids, the pure component on its own. So this temperature, I am sure you are used to choosing a value of 298 Kelvin. But the standard state refers to any temperature, any specific temperature where the tests were conducted. The pressure and the composition is the variables that is constant at the standard state. That is why all tables that list standard state values use the standard state symbol and then also specify the temperature to which it refers. Read Smith, Van Ness and Abbott page 136 3 times if you're still unsure. It's seriously important that you understand the concept of the standard state. In our equation for chemical potential, this standard state then refers to a specific temperature but at 1 bar or 1 atmosphere for the pure component. This refers to the fugacity of the pure component at 1 atmosphere or 1 bar, and each of these values must correspond to whatever temperature is used here. So if the standard state values for your component is given at 500 Kelvin in some weird table, this should refer to the standard state values at 1 atmosphere and 500 Kelvin. The caret here on the head of this symbol says this is now at the state and the composition and the pressure that you are actually experiencing in your reacting mixture. Now we substitute this equation into our condition for chemical equilibrium and sum that over each of our components in the reacting mixture. So now a very shortcut explanation of what you should make of these fugacity values that is given in this equation. For an ideal gas, we know that its compressibility factor is equal to 1, and subsequently we can calculate its specific volume just by considering the temperature and the pressure of that gas. For real gases, the compressibility factor can be either larger than or smaller than 1, depending on whether there are repulsive forces between the molecules or they have their size play a role, or it's smaller than 1 because of the attractive forces between the molecules. This implies that simply applying the ideal gas law will not result in the correct specific volume. So now the fugacity, and remember we are still considering just pure components, is a pseudo pressure that will make the ideal gas law true. And it can be calculated with a correction factor, the fugacity coefficient, multiplied by the actual pressure that the gas is experiencing. In a mixture of gases, and this is what this caret refers to, we are now considering what the effect is of the fact that it is now in contact with other molecules, unlike molecules with different interactions. If we had an ideal gas mixture, we can calculate the number of moles of component I if we know its partial pressure in that mixture as predicted by the ideal gas law multiplied by the total volume and the temperature of the system. For a real gas, we have to realize that the total volume will be influenced at that pressure by the fact that there are interactions between like and unlike molecules. Once again, we introduce a correction factor to compensate for the interactions between molecules. In this case, since it's in a mixture, this fugacity coefficient in the mixture is a function of the composition. So what you should realize is that for an ideal gas, the fugacity of the pure component is therefore simply equal to the pressure, and its fugacity in the mixture is simply equal to its partial pressure. We make the same analogy for liquids. For non-ideal mixing in the liquid phase, the fugacity in the mixture is given by its mole fraction times its activity coefficient, or its actual activity in that mixture, divided by, in the pure phase, its mole fraction, of course, is 1. For liquids that mix ideally, the activity coefficient is equal to 1, and this ratio simply reduces to the mole fraction of that component in the mixture.